Hello, good afternoon. All right, Carlos is muted. No, not quite. Okay, now he's muted. Okay, so sorry for the delay. My name is Jeffrey Gillan, and you tuned into NextGen Geospatial, the data science workshop series here at the University of Arizona, coming to you from the Science and Engineering Library. Today at NextGen Geospatial, we are going to cover kind of a different topic than what we've have been doing before. So let me just start sharing my screen and we'll get rolling. Okay, share screen. All right, participants can now see my screen. All right, so here we are at the course website. Let me just take this and throw it in the chat so you have it. This is the same course website that we've been using all semester. And let me just get a check. And can you see my screen? Ravindra, can you see it?
Yeah.
Okay, excellent. Thanks for tuning in. So let's go down to the schedule. All right, so today is April 16th, 2024, and we're going to cover a topic called containerized pipelines. Okay, so I'll just go ahead and click into the material and we'll get going with it. So for the next hour or so, we're going to be talking about what a containerized pipeline is. We're going to break down that term. We're going to try to keep this pretty high level, try to keep this as simple as possible, because this can be a complex topic. When I have taught this content before, I've done it over 3 or 4 hour time span. And so with this one, I'm trying something new. I'm trying to kind of introduce the concept of it and then have you guys run something yourselves, just just kind of as an example. And I'm sure you might have a lot of technical questions about what is going on or how to make it or how to do it yourself, and we can get to those. But this is just kind of a very general high level introduction of containerized pipelines. And as an example, we're actually going to run a containerized pipeline on GitHub code spaces. And we're going to be doing a little bit of drone imagery processing. So we're going to take drone imagery and we're going to do some photogrammetry processing. And then we're going to be doing some filtering to identify from a point cloud what are points that represent the ground and what are points that represent vegetation. Okay, and so this whole pipeline is automated. Literally, it's just going to be one little command and then the whole thing should run. And so that's the goal, is that this doesn't require too much technical know-how to run them. Okay, so as I go through this, please you can stop me at any time, ask a question, and we can clarify things. But again, we're trying to do high level and not get too deep into the weeds on this topic. Okay, so containerized pipelines. So let's break down that term here. So containerized pipelines, let's start with what is a pipeline? So I'm defining pipeline as an automated sequence of data processing steps, okay, where the output of the first step becomes the input of the next step. So it's simply a workflow. I'm sure everyone has done some kind of workflow in their life. Not necessarily doesn't have to be software data processing. How do you how do you mow the lawn? Well, step one, I have to get a lawnmower. Step two, I have to fill it full of gas. Step three, you know what I'm saying? So when it comes to pipelines, it literally just means a sequence of steps to go from the input to your desired output. So it's a very general thing we're trying to describe here. When it comes to software development, usually we start with input data, and then we have could be multiple processing steps to get to the final output. So that's how I'm defining a pipeline. It's simply a series of steps to go from beginning to the end. All right. So for the purposes of today, though, we are interested in talking about sequential processing, but between multiple types of software. So throughout this course, I have showed you guys a whole lot of Python scripts, right? You could call a Python script a pipeline. You know, it has a series of steps to go from the beginning to the end. So you could call that a pipeline. But for today, we're talking about, let's say you want to, process some kind of geospatial data, but it requires different types of software. One step might be Python, another step might be in R, another step might be in the command line, a command line tool of some kind. And so that's how I want to define it today, is just linking a sequence of steps that come from different kind of computing ecosystems or software environments. Because typically you wouldn't run R, right after a Python script, but there is lots of software options out there to enable just that. So that's what we're going to try to do today. The reason why I think this is powerful is that in my world of geospatial data processing or drone imagery analysis, some of the best tools may be from different ecosystems. I might have a great photogrammetry processing script, but that's a command line tool. But then I have a really great filtering script in R, and then finally a great classification script in Python. And so wouldn't it be great if I could just link those all together in an automated fashion? So that's kind of the goal today, is to introduce that. So they're saying there are several types of software to kind of do these pipelines. Ravindra, go ahead.
So Jeff,
Mm-hmm.
so as you go from input to output, so when you run it on your system, the tools that needed to go from, like, for processing step 1 or 2 or 3, are we going to have the same tools available when we do this pipeline?
Yes. Yeah. So the pipeline we're going to run together hands-on is on GitHub. And so it'll all should be running the same thing. And we're going to be using GitHub code spaces as the actual computer to run the pipeline. So in theory, it should all be, what I do should be the exact same thing as what you do. So we're going to be doing this pipeline today using a software program called Docker Compose. Okay, there are other pipeline or workflow management softwares out there. There's a whole lot. Some of the most popular ones include Nextflow. There's one called Makeflow and SnakeMake. So these are all software programs that can, create simple or very complex processing pipelines where you go from one step to the next, to the next, to the next, to the next, to the next. Kind of getting as complex as you want. But for today, we're going to keep it real simple. Okay, so that's what a pipeline is. So next, let's define the other term, containers. So containers and reproducible code. Okay, so a software container. So the scenario is, so first, I'm a really big proponent of open science. In other words, I want to, if I create computer code to do something cool, I want to share it with people. And vice versa, if someone else creates some really great computer code, I would like to use it and not have to create things from scratch. And so in the world of trying to share computer code with each other, there can be a lot of great challenges to making someone else's code run on your computer. Okay. Some of those challenges could be hardware differences. We like to work on different operating systems. If you write code and it works on your Windows machine, is it really going to work on my Mac? I'm not sure. And then the real killer is all the software versions of everything. If you are running something in Python and R, chances are there is many software dependencies to making anything run. And every single one of those software dependencies has a version, right? And all the versions have to be all aligned perfectly to get typically one script or a piece of code to run properly. And so it's very easy to enter this software version dependency hell. where you just can't get anything to run because the versions don't match how they should. So I'm saying it is difficult to share code with someone else and it just runs. Usually you're gonna have to install this software, uninstall that software, really have to like curate the environment just perfectly to run your colleague's code. And that's a great challenge. And so one solution to getting around this, it won't work on my computer problem is to use something called software containers. So what are containers? So a software container is a standard unit that packages up the code, but then it packages up all the software dependencies within this package, okay? And so that can be all packaged in what we call a container image, and then that container image can then be ported over to someone else's computer. And the idea is that it just runs without having to to do the traditional installation on this other computer. So that's the general idea of what a container is. You're not just sharing code, you're sharing code, but with it, everything that is needed to run that code. So a useful analogy that I like to think of is shipping containers. That's the typical analogy people use. So with shipping containers, we can move cargo all around the world in a standard way. And so the shipping container can be offloaded and executed anywhere as long as that destination has a shipping port. Okay, so that's the analogy. But in our world of software, the shipping port is software called Docker. So if I have a software called Docker on my computer, in theory, I can run any Docker container that anyone in the world made. And so with this system, you can share code, and I can send it over to Carlos. I can send it over to Ravindra. And if he has Docker, he can just say Docker run, and it should just run the code. And Ravindra or Carlos would not have to install the environment. They wouldn't have to curate all the software dependencies, all the things like that on their computers, because I gave it to them in a package called a container. So containers can be challenging and might take you a while to kind of wrap your head around it. And the easiest thing to do to understand them is just run several of them so you get the idea. But software containers are a type of virtualization. So perhaps you've heard of virtual machines. Virtual machine is when you take a physical computer and you can partition it or divide it into several virtual computers. And each one of those virtual computers can run just like a computer, right? So it's a VM or a virtual machine. A container is sort of like a virtual machine, only it's a lot smaller, it's a lot more compact, and it only includes code and like the software to run usually a specific application. And so they're a lot smaller in size, and they can be put on the web in hubs where people can download them, kind of like GitHub in a way. Instead of just sharing code, you can share code with all the things necessary to run that code. And that's what we call a container. So why do we use containers for reproducible science? So in the end, that's really the goal, is if I make some really nice analysis code, is that I can share it with my friends and my colleagues, and they can just use it and build on top of it and not have to start from scratch. So some of the advantages is that it has environmental consistency. I think we've already kind of gone over this. The fact that hopefully we can overcome the it worked on my machine, but it won't work on your machine problem. Yep, it becomes easy to share. And it's platform independent. So in theory, it should be agnostic of operating systems. So if I have a container that was built on a Mac, the idea is that that container should be able to be run on any other computer in the world, Windows, Linux, anything. And there are some caveats to that statement. We don't need to go over it right now today, but that's the theory, is that once a piece of software or computer code is containerized, then it's portable. It can then go anywhere and just be ran. So I mentioned before that Docker is the most common container software. There are other container softwares out there. There's Aptainer, there's Singularity, and Aptainer and Singularity are popular for deploying software on high-performance computers, or HPCs. Docker is not really for HPCs. Docker is for, your computer or your colleague's computer, things like individual computers. Okay, and another thing to be aware of is Docker Hub. So Docker Hub is just like GitHub. Docker Hub is the world's largest repository of container images. So we use this terminology, container and container images. For today's purposes, let's not try to distinguish them. Let's just call them the same thing. Containers, images, same thing. So Docker Hub, yeah, is just like GitHub. It's a place online where you can have your own account and you can post your containers. And then any of your colleagues can then download those containers and use them on their computer. And vice versa. I can search in Docker Hub and find containers that other people have created, and I can just use it. I can run it. I get a lot of value out of Docker because perhaps some of you could commiserate with me, is that installing software on your local machine can be a headache. Sometimes it works really easy. Other times you can struggle for hours or days figuring out why your installation for software is not working out. So if you're using Docker, that can be a great way around that problem. Let's say I'm using QGIS, and this is real. I've struggled for literally months with installing QGIS on my Linux desktop computer. Why? I don't know. I spent forever trying to figure out what the problem is, but I can get around it because QGIS is available as a container, a Docker container. And so since I have Docker on my machine, I can just use it in a Docker container way, and then it works on my machine. So there are a lot of advantages to software containerization. Okay, so before we get into the hands-on example, is there any questions out there, kind of high level, about what we're doing? Containerization or pipelines or containerized pipelines? Okay, well, what's that? Okay, Ryan, Fireship. What is Fireship?
It's just a YouTube account. They do highlights on technology stuff all the time. So it was like, Docker in 100 seconds or, quick tutorials. So
Wow, that's nice. I'll have to
yeah.
check that one out. I'm always looking for good YouTube educational videos.
Fireship's edutainment.
Edutainment. Okay, great. Yeah, I'll check out Fireship. Yeah, okay. So other than that, I think we can do a hands-on example. Well, let's describe what we're doing here in this hands-on example. Okay, so we're going to run an example of a containerized pipeline. So for our example, we're going to be processing drone imagery that I collected over a golf course in Phoenix, Arizona. And I did this last March. So March 2023, I collected this drone imagery. And here, this graphic here is showing you kind of how the pipeline or the workflow goes. It's one direction. It starts on the left and heads to the right. So the first thing I did was collect the data via drone. And these are just JPEG still images. Let's see, down here, I talk about some of the specifications. So the drone was flying at about 60 meters above the ground. For our example, there are only 41 images. And so these images are overlapping. Overlapping meaning, if you look at the image, you can see the same tree or the same feature in multiple images. And so we do this overlapping thing for photogrammetry purposes. So if we have a series or a bunch of two-dimensional drone images that are overlapping, we can use photogrammetry software to stitch it into a three-dimensional model. So that's what we're going to do in this pipeline. So it was a DJI Phantom 4 RTK drone. The camera is just a regular red, green, blue 20 megapixel camera. So for the real project, I probably collected 400 or 500 images of the golf course, but that would take a very long time to run as an example. So I just selected a small subset of 41 JPEGs. Okay, so that's the data collected. That's the data we're using, 41 images of a golf course. Yeah, Ravindra.
Jeff, sorry, Ravi, but what's the size of each image?
I'd have to look. It's like, I don't know, 3,000 by 5,000 pixels. Is that what you were asking? Pixel
Like,
size?
like I was wondering about the megabytes, in terms of megabytes, how much they?
Yes. Once I go to the repo, we can take a look. I think each image is 8 megabytes.
Oh,
And I
okay.
think altogether, 41 times 8, it ends up being, I don't know, a couple hundred megabytes. So yeah, drone imagery is heavy in general. It usually is many bytes.
Sorry to ask you one more question.
Sure.
How much does it cost you to do one survey?
Well, that is definitely a tangent. We can talk offline. That's
Okay.
a whole lot of variables involved in surveying with drones. And yeah, let's chat about that another time. Okay, so that's our input data, some drone imagery. And then we get to our actual processing. So the first step of the processing, which is in its own software container, is called Open Drone Map. So Open Drone Map, and I have the link here if you want to learn more about it. Open Drone Map is an open source photogrammetry software package that takes a series of overlapping images and does some real magic. It's called structure from motion photogrammetry. And it outputs imagery products such as three-dimensional point clouds, which are really beautiful three-dimensional models. You can also create digital elevation models and orthomosaics. So Open Drone Map is very nice, and it's also completely free and open to use. So for our pipeline purposes, the output of the photogrammetry is an unclassified point cloud. So it's just a point cloud showing a portion of hole number 17 at the golf course is what it is. Okay. And so the next step, so we take our unclassified point cloud, which is the output of step 1, and then that becomes the input for step 2. So step 2, it uses a command line tool called PDAL. Okay, so PDAL is also containerized within itself. And so PDAL is it's developed by Howard Butler and his company, and it's very similar to GDAL. GDAL is command line software that's in most GIS software out there in the world, and PDAL is similar. It's a whole bunch of scripts and tools for manipulating and analyzing point cloud data. So the purpose, or what I'm using PDAL for, is to do a filtering or a classification procedure. And so from my point cloud, I'm going to try to identify which points represent vegetation or, trees and shrubs, and which points represent the bare ground or the grass, like the ground. Okay. The specific filtering technique I'm using is called cross simulation filtering. We're not going to go into the specifics of that. But so yeah, PDAL is basically going to take our point cloud and classify it into two classes. It's going to be trees and shrubs, and then ground. Okay. Okay, probably just more we use Open Drone Map and PDAL. Okay. Do that. All right, so for this pipeline, those two steps, it's just going to be basically two steps. Each of those are individually contained using Docker. And then we orchestrate this multi-container pipeline using something called Docker Compose. Docker Compose is it's like a one single YAML configuration file. It's just a file that specifies we're going to run these two containers in sequence, and I can show you what it looks like here in a minute. Why DJI Phantom 4 RTK? We can get into all these drone questions a little bit. Once I hit go with the pipeline, I think we'll have 8 minutes for it to process, so we can maybe hit some of those drone questions. Okay, let's run the pipeline. So the output of this is going to be a classified point cloud via drone. All right, so let's go to the repo that has the actual pipeline. And it's right here. I call it Geospatial Pipeline. Okay, it's yep, Ravindra.
Jeff, can you please go a little bit slow when explaining this pipeline thing?
Okay, which specifically are you having trouble with?
Not trouble with, but the geospatial pipeline, the script that we have, the GitHub script. While explaining, can you please just go slow, because I'm really interested in. If you go really quickly, I won't be able to grasp anything.
Right. Okay, I got it. Try to do it as slow as we can. Okay, so here we are in the actual pipeline. So this repository actually contains what we need to do this pipeline, and that includes images. So if I click in here, here are all my 41 drone images. They're all JPEGs. Let me just click on one to give you an idea. Okay, here's one image. So this is Paradise Valley Country Club up in Phoenix. And here's just one image. It is 8.59 megabytes. So hopefully that helps just kind of get a visual of what the data is we're looking at. Okay, here's another one. And so this drone imagery, some of it is nadir and some of it is oblique. Nadir means the camera is pointing straight down, and oblique means there's an angle to the camera. And for really good photogrammetry, both are very useful. Just add them all together and you can make a very nice three-dimensional model. Okay, so that's our raw data. Let's just hit run. And then we can talk through some of this stuff. Well, before we do that, we have to actually get our processing engine up and running. So in my instructions here, I say you can clone this repository to your local machine if you want to process it locally. I'm going to suggest we just do it on code spaces. So alternative, that's what we're going to do here. Step 1, alternative. So if you watch what I'm doing, okay, from here, we can start our own virtual machine right here in GitHub. It's called GitHub Code Spaces. So I'll hit this 3 dots here. New with options. Okay, and just keep in mind, this is being recorded, and I will, of course, share this in a few weeks that you can follow along. Okay, so I'm about to create a virtual machine. Thank you, Microsoft, for making this possible. And I want to choose a big machine, 16 cores, 64 gigabytes of RAM. So anyone with a GitHub account should have access to doing this. I'm sure there are limitations on how much computing you can actually do, but they are giving it out for free, at least the teasers. So I'm going to create a little virtual machine here. This should just take a moment. And when you launch a CodeSpaces virtual machine, it puts you right here into VS Code, which is a great integrated development environment. Ravindra?
Joe, I have a question. So JPEG images that you have, are these just simple like you say like drone took an image? It is simple like location coordinates, or it does have any like additional like elevation too? I'm not familiar with the drone
Okay, yeah, so
images.
the drone images are just JPEG images. They were collected by a drone, and so with the GPS, and so in the metadata of the image are coordinates, or like where the center of the image. So we know where that drone image was, snapped on planet Earth, and there's other metadata included from the drone. But that's not all that important. With these great photogrammetry software programs, we just need a whole lot of overlapping images, and then we can make beautiful 3D models with it. Okay, so we have here our virtual machine. Thank you, CodeSpaces. So here I am at the Linux command line. And once you launch a CodeSpaces, I'm just immediately within the repository that I launched it from. So if I do ls, that just lists like what material is in that folder. All right, and it's just showing me what's in, so do I need to zoom in, or what do I need to do?
Increase your phone.
Okay, I can do that.
Got a license, a README, a YAML, and some images. Is that right?
Yep, yes, sir.
And the assets, whatever those are.
Assets is just like a graphic, like I had the pipeline graphic. That's what the asset is.
Gotcha.
Yeah, code space screenshots. Oh, I have something called crap markdown. Not important.
Yeah, get ignore.
You could ignore that, yeah. Okay, so I'm just reading the README here, which is the same thing that you just saw earlier. Go to my instructions. Okay, all I have to do is type docker compose up. That's all I have to do. Docker compose up. And so when I hit this command, it will launch this containerized pipeline, and it should take about 8 minutes to do so. And then at the other end, we will have our imagery product. We'll have our classified point cloud, and then we can look at that point cloud in a website viewer. Okay, so Docker compose up. Let's see what happens. Okay, so you see polling. So that means it is polling containers, those two containers, the one that runs OpenDroneMap and the one that runs PDAL. It's pulling those off of Docker Hub, because that's where I have them parked for anyone in the world to just use. And so that's the first step, is it pulls it, it downloads it here to the virtual machine, then it will start running it. Let me start a timer here. See how long it actually takes. Okay, so it's just gonna spit out kind of information, not very useful information for a while. Timer. Stopwatch. Okay, started the timer. I'm just curious how long this takes. I tested it with different size virtual machines, and I figured that the very largest was probably the best. It takes the shortest amount of time. Okay, so while we're waiting, we can go back to our repository here.
Quick question. I was looking at this ahead of time, but I did not see what we're looking at right here when I was reading through. I don't know if I was on the wrong page. I saw the, the ocean vessel container ship, but I didn't see that pipeline.
Okay, that's because I have a link to it.
Okay.
Yeah, so this is what you saw. Yeah, with
Yeah, I saw that part.
that's the
Yeah.
main content. And then we get down here and I'm like, run the pipeline. Then I give you a link to a different repository, and that's where the actual pipeline stuff is at. This one right
Okay.
here.
Okay.
So if you go there, then you'll end up here. Okay, so while that is running, we can talk a bit more about this or answer any questions. So I am currently in the process of doing container image 1, which will then pass on to container image 2, which will then create my classified point cloud output. Okay, to run that, all we did was do Docker compose up. Then we're going to visualize it. And that's just a screenshot of the visualization that we're about to see in a little bit. Okay, so Ravindra or anyone else, do you have any questions so far about what we are doing?
Nothing yet. Thank you.
Okay. So on the screen, you're seeing just a bit more details about each of the containers. So the first one that we've talked about, Open Drone Map, it is a structure from motion photogrammetry software package. It's all completely open source. And it's going to output a point cloud. And then it'll pass on to container 2 using PDAL. Okay, I've talked about that. And so this here is the Docker Compose YAML. So this is the configuration file. This is all that was needed to connect the dots and create this sequence of containers. Now, creating Docker Compose YAMLs or Docker files, that's when things start to get a little bit more difficult. It's very, very easy to run Docker containers, but then to build your own is kind of another thing and can be challenging. Just like any kind of coding exercise, where do you start? How do I go from nothing to having something that's going to work is always challenging. So it's about begging, borrowing, and stealing from YAML files that other people have built on.
Amen.
Yeah.
So for instance, this Docker Compose YAML services. So when I say services, those are the 2 containers we're going to run. The first one is ODM, or Open Drone Map. The second one is PDAL. And probably the most important thing in this little configuration file is this depends on ODM. So in other words, the second container is not going to run until the first container has completed successfully and outputs the unclassified point cloud. Let's see here. Okay, so yeah, I can answer some other drone questions here. How are we doing? Looks like it's still running. Okay, Henry, how does the open source structure from motion compare to Pix4D and Agisoft products? So I've used all of them. I would say Agisoft is still my favorite. I think commercially, it makes the best products. What Open Drone Map has going for it is that it is open and free and not behind paywalls like Pix4D and Agisoft are. I mean, if you're doing real important work, I would still probably would stick with Pix4D and Agisoft. I have not explored Open Drone Map enough. I've not really benchmark tested it to know, but I have been hearing a lot of good things from a lot of kind of open source researchers that it is a pretty good option, but maybe not quite at the same professional level as Pix4D or Agisoft. But I think Open Drone Map is still Still pretty decent. How is our processing going? Still going. Okay, we're at 5 minutes and 40 something seconds. A couple more minutes and this should work. Yeah, you're welcome, Henry. Okay, and then other questions about just like drone surveying in general. You know, that is a big conversation. How much does it cost? You know, like anything in life, it depends. depends on a lot of variables in terms of how expensive is your drone, what kind of area, what size of area you're trying to cover, how high are you flying the drone, things like that can be hugely important in terms of, you know, cost of a survey. Ryan, why the DJI Phantom 4 RTK? To me, that is still the most performant, affordable drone ever made. It is absolutely incredible. DJI really perfected the drone with the Phantom 4. And then when they added in the RTK component to it, that opened the door for to fly very large areas without having to include ground control points. And that is in terms of, you know, cost savings is enormous. So I flew the Phantom 4 RTK. I still have one actually, but I flew it, you know, many times, you know, hundreds of times. RTK stands for real-time kinematic GPS.
Okay.
And so the GPS of a drone is usually not going to be super accurate. It could be accurate within, you know, horizontally 4 or 5 meters, vertically probably worse than that.
Wow.
Real-time kinematic GPS is about getting a very precise location, 3-dimensional location of the drone up in the sky when it snapped that photo. And that leads to very accurate image products in terms of georeferencing and scaling. And so RTK is a huge cost savings because you don't have to go out and survey a lot of targets on the ground, which is typically how people would make very precise imagery.
So it's like a $6,500 drone, but it's going to
Yeah,
save you on
yeah, when I
on the
got it,
back.
it was about 9 or 10 grand. I got it in 2019, like when it first came on the market. Is it, are you seeing it for 6 nowadays?
Yeah, on the DJI store,
Okay.
6.600.
It's like, to me, they perfected it with that. It's, I can't find something that's better in terms of just red, green, blue imagery. And for bang for your buck, it's just fantastic.
Wow.
Ravindra, did you have any questions?
Yeah. So Jeff, I saw you could see the canopy, but is there any way we could create like suppose there's a tree? If you could see tree structure with the drone images.
Are you talking like the basal area of the trunk of the tree?
Like I'm more interested in canopy structure, like as you go down from top to bottom, like how the canopy, like what is
Yeah,
canopy say?
so yeah, photogrammetry can do a pretty good job. But if you really want like top to bottom structure, LiDAR is probably a better technology in that case. But yeah, I've done very good structural reconstructions with just drones and photogrammetry. And it is so much cheaper and easier to do than LiDAR. LiDAR is expensive.
Yeah.
Okay, so let me get back to what we're doing here. So my processing finished. It took about 9 minutes. That's good. Okay, so if I go over here in my files here, you notice all of a sudden there's a bunch of new folders called ODM underscore something. So those are all generated from OpenDroneMap and the processing I did. So if I go into ODM georeferencing, I'm going to find some things that I created. So let's go to this one here, model.copc.laz. Okay, I'm going to download it to my machine, my local laptop here, and then we're going to visualize it. Going to a viewer called viewer.copc.io. This is a nice point cloud viewer that's just free to use. Okay, so the model that I just downloaded from my code spaces, I'm just going to drag and drop it in here. And here's what we just created. Please never mind the quality of what we just created. The purpose was to make it run fast. And so I greatly reduced the number of images and the processing quality just to output something. And so this viewer, so here we are in a golf course, Paradise Valley Country Club in Phoenix. And down here is what we just created, which is a three-dimensional point cloud from photogrammetry. And I can change the color to red, green, blue, so you actually see what it looks like. So we have a golf course here. We have some trees there. You can tell they're trees. They're not beautiful looking, but again, that's a quality issue because I needed this to run quickly. Okay, let's see. Okay, Henri, probably a good idea to explain the mount point in the container if your data lives somewhere else. Yes. We'll get to those technical details in a little bit, but thank you for that. Okay, so this is the first thing we outputted from OpenDroneMap is just a three-dimensional point cloud. And if you go over here, you can see the kind of 3D creation of some of the nearby houses. And this is very low quality stuff. The stuff that I actually put time and effort into are much, much better looking. If I go to class,
using all the same methods and tools,
all the same methods and tools, I would just
time is the only difference.
I would just change the parameters to higher quality, which would take much longer.
Yeah, it's a time commitment difference.
Exactly. Right. That is all just time. Okay, so if I go to classification, I get nothing here. So I have no classification. All right, so then let's go back to, okay, and so here's another thing I outputted, and this one's filtered. So I'm gonna download that. That is what I created using the second step called PDAL. And so it did a filtering or a classification to identify vegetation from ground points. And let me just drop it in here. Okay, so you can immediately see that now we have two classifications. The maroon red looking color is been classified as ground, and the white area has been classified as vegetation. Just go to RGB. So we essentially, it's the same point cloud, but we just now have a classification involved in it. Okay, so that's basically what I wanted to show you guys is that it's not too difficult to create these pipelines where we can combine multiple types of software into one kind of cohesive automation. In this case, we started with OpenDroneMap and then passed it on to PDAL. Just as easily could be Python followed by R followed by GDAL. Kind of any software you want can be linked together and containerized. So I'm a big fan of containerization because then I could just, through GitHub, I just made this open. So anyone can go to this GitHub repo and just run the thing and not have to set up the software environment on their own computer. And so we've got about 9 minutes left. Any pressing questions? So again, this is about being high level. We're not going into the weeds about how Docker containers were made exactly. That's kind of like a whole nother ball of wax. But does it make sense in terms of what we did in terms of running a containerized pipeline?
Definitely.
Okay.
I'm curious if there's time to cover like use cases or products or
Related to
applications.
drones or for pipeline?
Well, yeah, I guess the whole process from the drones to the pipelines, like
Well, there's a whole lot of applications for drones, you know. Most of what I've been involved in is around surveying land for kind of ecology purposes or agriculture purposes or civil engineering purposes. You know, we can make a 3D model of the land and then make measurements from that 3D model
the
in
measurements,
ways,
yeah.
yeah, in ways that you can't really measure from the ground. You know, if you're on the ground, how do you measure the volume of a tree? Or how do you capture the complexity of a tree? It's
Right.
very difficult. But if you have a drone, you can 3D scan it with photogrammetry or LiDAR and then measure anything you want. You can measure crown area. You could try to estimate biomass. You could try to estimate leaf area index, the height of the tree, the width of the tree. You can do that all with drone imagery and then analysis afterward. Next week. Yes. Okay. So any other quick questions? Okay, so next week, so a week from today, we have a special guest. So Austin Stone, who is from Planet, is going to be here. Well, he's going to be on Zoom, and he's going to talk about kind of everything Planet is doing and what's available here on the campus of U of A. In the very first workshop we did, we talked about data APIs, and we use Planet Satellite Imagery Company as an example. So we have a very large campus license, so anyone at U of A can get all kinds of Planet satellite imagery for free. And so Austin's going to talk about everything, all the different imagery products that are available. And there's a really exciting new software or like analysis platform that Planet just came out with called Insights. So think of this as kind of like analogous to Earth Engine or Microsoft Planetary Computer. It's called Planet Insights, and they create this whole cloud-based analysis platform. So I'm kind of excited to look under the hood and see what it can do. So Austin Stone is going to kind of share all that stuff with us next time. And then because of popular demand, the week after that, I'm going to do another drone imagery analysis session. And this is specifically going to be deep learning to identify. I'm going to show you examples how to identify trees. There's a really great deep learning Python library called Deep Forest. Some colleagues of mine created. And so we're going to go over how to use that. And they have, it's super simple. And they have pre-built models that we can just, you can just give it your image, and it does a pretty good job of identifying every single tree in the image. But then, you can do a little bit of your own training to then fine tune that to your area of interest. And so I'm learning right now how to best use Deep Forest. And then so 2 weeks from today, we'll have a little bit of a session on deep learning using Deep Forest for drone imagery.